In the last part of my tutorial, I will show how we can use the relational parametricity theorem and the relational naturality law for cases where naturality laws are not enough. The Yoneda lemma does not apply. The wedge law does not hold, holds but does not give enough information. And here's one first relatively simple example where we consider the following type. Now, this type signature is for all A as a function of this type. Now, E here is a fixed type. Let's say it's integer, doesn't matter. It's a fixed type. We're going to just keep it like that. Now, the Yoneda identities do not apply because it is not in the form of a Yoneda lemma, which must be, for example, like this, R to A to some type constructor, where R may not be A itself or may not depend on A. Now, if it does, then you cannot do anything with this type signature. So this does not work. The naturality laws, this is not a natural transformation either, so this does not work. Naturality laws are not applicable. The wedge law can be derived and it holds, but it does not give enough information to derive the properties of this type. So we have to go back to the full generality of the relational naturality law. So consider a value P of this type, and the relational naturality law says for any P of type P of A, for any Q of type P of B, P and Q must be in this lifted relation R. So let's write down what that is. We translate the type into lifting combinators, the relation combinators. So that's a function of a function between R and R, because each type parameter A is just replaced by this arbitrary relation R. And then there's a pair sum of identity, because it's a fixed type translated into the identity relation of type E to E. And R. So let's write out what that means. For any K, so let's write out what that means. So that's a relation between functions of type A to A and B to B. So if these two functions are in this relation, then these are in that relation. Okay, well, that is kind of not easy because R is an arbitrary relation. We need to use a specific relation for which we can simplify this condition and make progress in the proof. So in this case, the trick is to use an empty relation. So an empty relation, which I denote by the empty set symbol. The empty relation is such that no values are in that relation. So A, B in empty relation never holds for no A and B. So that's what we use. And let's write out what it means to have that K and L in that relation. So for any A and for any B, if AB is in the empty relation, then K and A, K and of B are in the empty relation. But this never holds. So this if is vacuous. If something that never holds, we don't care what happens then. So this is actually always true for any two functions. So that means for all functions K and L, the functions are in that relation. So all functions K and L are in that relation. So let's write out what that means for the lifting R sum. So for any K and L, either P of K and Q and L are on the left, and then they are both equal, some value left of E with some value E, or P and K and here this is Q of L, P of K and Q and L are on the right, and then X and Y must be in the empty relation, but that can never happen. So this or here is always or false. Right? This can never happen. So this is false. The only possibility is that both P and K and Q of L are equal to some left of E with some fixed value E that doesn't depend on K and L, which means that P and Q must be equal to each other, must be constant functions returning some fixed value of type E. So we have proved essentially that this entire type is equivalent to the type E, because the only way to implement value of this type in a fully parametric code is to return a fixed value of type E always on the left and ignore this argument. So that's a type equivalence that we can then prove using this trick by using the empty relation and the relational parametricity law. Now, this example is a little maybe artificial. The next example is more interesting. It's the so-called church encoding of recursive types. Now, this is a big topic. I'm limiting myself to proving the properties that are useful for practice. Recursive types are defined by induction, usually, but this can be equivalently written like this as a type equivalence between a type T and some type constructor applied to the same type T. So you say type T is equivalent to some type expression containing T itself. And in this definition, the type constructor S is called a recursion scheme, and it must be covariant in its argument. There are really some troubles when it's not covariant, and it's never used in practice in that with anything else than a covariant type constructor. So what is the isomorphism in this type equivalence? The isomorphism must be given by two functions of type signatures S to T and T to S. And these functions may be called fix and unfix. So the two functions must be inverses of each other. So fix and then unfix must be identity. Unfix and then fix must be identity. So that, if that is true, then this T is called a fix point of this type equivalence or type equation. But this is just a jargon for saying that T is equivalent to S of T using these functions. So here's an example. If T is list of some type R, then this is true with S of A given by this type constructor. So if you think so, this is either none or it is sum of R and then again same A, right? So same T. So either none or some pair of R and something else. So this, if you expand this, then you get either an empty list or a list of one R or a list of two R's and so on. So this is equivalent to the definition of the list type by the usual way. So the non-trivial property here is that there is a different way of representing this recursive type, namely through fully parametric functions of higher order. And this is the recipe. This is called the church encoding of the recursive type with recursion scheme S. Now, this is a very difficult type signature. It's a higher order function. It's difficult to reason about. And so it's a non-trivial result that actually this type CT is equivalent to a solution of this type equivalence. So that, so I'm going to show why that is so. Now, this type can be written with Scala 2 traits. And so this is a Scala 3 syntax, but with Scala 2 traits, you have to write it like this, where you define a function with type parameter inside the trait. And it's important that the type parameter is not visible outside this trait, which means that the same value of this type can be used with any type parameter A inside. So you can call this function, which I call fold for reasons explained shortly. This function can be applied with any type parameter. So that is important. One value of type CT has inside it a function that has an arbitrary type parameter. So what is the intuition about these types, and what is this S of A to A, and so on? Let's consider the list type. A function of this type, now S for the list type is the option of a pair. So the function of type S of A to A is equivalent to a function of this kind of form, where it has a pattern match. Either it's a none, and then you have to return some fixed value of type A, or it's a sum of a pair RA, and then you need to return the value of type A that you might compute using this R and A. So let's call this compute next. Right, so this data that you need in order to define this function is equivalent to a pair of A. So you need a fixed value of type A, and you need a function that takes a pair of R and A and returns A. So the data in this type is equivalent to this data. Notice this is exactly the argument data of the foldLeft function of list. The foldLeft takes an initial value and then an updater function. This is updater. And it returns the value of type A again. So we can write down the type signature of foldLeft like this. So this is the fold data. This is the argument data of foldLeft, and this is the result. Now, for lists, usually folds mean that you aggregate the list data in some way into a single value, and you update that value, iterating over all the list values. Now, for arbitrary recursive types, there might not be the same iteration, or it might not be the same procedure. But essentially, it's a fold, a generalization of the folding operation, or an updater of data. So this data of type S of A to A is some kind of fold data or updater function, generalized to an arbitrary recursive type. Now, it does not have the same meaning as for lists, maybe. Like for trees, it may be still iterating over the tree, but for other recursive types, it might not be. So the intuition behind the church encoding is that we represent a list via the fold function. The fold function needs to work for any type A. And the only way that you can make such a fold function is, in other words, the only way that you can fold, give a value of type A from this data is when you have a list of values of type R. Then you can use fold on this list, and given any fold data, return the result of type A. So you're supposed to be able to create a result of type A from fold data. And the only way you can do that in the same algorithm for all type parameters A is when you have already, you're holding on to a list of type, a list of R, and you're just using foldLeft on that list. So that's the intuition. And for other recursive types, it's not going to be folding, but it's similar. So it's kind of a function that extracts values from the recursive types. And these values can be of any type A, and you're supposed to be able to do that given this data. And the only way you can do that is when you have a value of the recursive type. So that's the intuition. The paper by Wadler, Recursive Types for Free, explains a little bit more detail about how all this works. I will adapt that paper and simplify its arguments a little bit to give the derivation. The first step is to implement this fix and unfix functions. Now, this is the Scala code for them. It's a little complicated. So how do you implement a fixed function? You're supposed to take S of t and go to t, and t is the ct instead. So this entire thing, this is ct. So how do you get this out of S of the same? Now, you have to apply, so you're given this fold data, and you have to apply this fold data to a function that gives you the value a. So what is that? What is that function going to be? Now you take this SCT, it's a functor, so it's covariant, so it has a map function. It's map function you can use in order to convert S of CT into S of A, because CT can convert any fold data into A. And so that's how you do that. And then the map over that gives you a function of type S of A to A, and then you apply, it gives you a value of type S of A, and then you apply that S of A to that value, and you get the value of type. So you use SAA here twice. That's not recursive, that's just SAA is the argument, which is this, of this type, and then you just write this code. It's a little involved. The unfix is a little easier. You just take CT, this value CT, and you apply with the type parameter S of CT in order to get S of CT out of it. And then you just need to provide fold data, and the fold data is this fmap S of fix. Now, that by itself is a lot. So this code is not trivial. But it's then necessary to prove that fix and unfix are inverses of each other. So if you just substitute one into the other and do fix and then unfix, you will get a big code expression that's not obviously equal to identity, and the other way also. So you need to use some kind of law in order to prove that they are equivalent. And actually, the law is that you are only allowed to use fully parametric implementations of this function. So the value of CT must be fully parametric function of this type. So let's write down the relational law of those values. If we do that, then for any relation R, for any P of type S of A to A and Q of type S of B to B, when they are in the relation lifted to this, and I'm writing out that relation, which is for any arguments, if the arguments are in lifting to S, then the results are in R. Then we will have the values of the function CT on P and Q are in R, because this is just A. So this is the relational law. It's too general. We're going to specialize it and put a function graph instead of R. So let's arbitrarily choose a function f and substitute it in there. Then if we put all that as function graphs, this is a function graph. This is going to be lifting of a function to a covariant type constructor. So that's just a covariant lifting, fmap S. So you have this condition for any P and Q, which is fold data of types SA to A, SB to B. When this fold data satisfies this equation, then we must satisfy that equation. Now, this is not so easy, because it's not just a single condition for single equation for CT. It's for any P and Q satisfying this condition, and this condition actually can be written like that. So it's a commutativity diagram, commutative diagram, where you do first P and then F, or like this, and this must commute. So the folding data for S of A to A and S of B to B must be compatible in some way so that this diagram commutes. So this function f must be compatible with this folding data in this one. It's not a trivial condition. So then you have this thing. So this law is quite general. It still has a lot of freedom. We have arbitrary P, Q, and F. But now at least it's some equations, and that's what we're going to use. We're going to use this kind of law. We could then just substitute fix and non-fix and prove the isomorphism laws directly via this. But so this is what I do in my book, but this is not very illuminating. This does not explain why this works in some sense. So we instead use tricks. And so these tricks are in the paper by Wadler. And I'm just going to adapt them and simplify a little bit. So the trick is first to prove the property that is called the initial algebra property. Now this doesn't explain anything at all, these words, initial algebra. They come from category theory. I'm not going to explain what that means because actually this is not necessary to explain what that means. We don't need to know any category theory to prove this property. We just say this is fold data, and the property that we're going to prove is that for any fold data, there is a unique function that maps our church encoded type to this B type. So this function is a result of folding. So for any fold data, there's only one way of extracting the fold result. That is this property that we're going to prove. So it's kind of a uniqueness of folding. For any given fold data, there's only one function C, which depends on this Q. C of Q is this function of this type, which extracts the final value of type B out of this church encoded structure. And this function must satisfy the same kind of diagram. It must be compatible with the fixed point structure or the type equation of our type. So this is a very similar diagram than that was here. Certainly not by accident, but essentially it means that this folding function is compatible with the recursion structure. So this diagram summarizes the recursion structures in the fold data and in the type CT. The code of this function is pretty straightforward because the type CT itself is defined like this. So for any folding data, I can give you the result of the fold. That's essentially what this type says. And so we just apply that function with type parameter B, and we get the result. So we have one code that implements this function, but we want to prove that there is only one such code, that there is no other way of folding. That's a non-trivial property. So the first thing we need to prove, actually, is that this code satisfies this diagram. We need to say that not just some way of folding, but this way of folding must be compatible with the recursion structure via this diagram. So let's prove that this code satisfies this diagram. For any value SCT, we need to prove this, which I'm just writing out this diagram. Now, if we substitute what C of Q is by definition, and we have this, and here we have this. So now we need to prove that this is equal to this, but that's actually the definition of what fix is. If you look at the definition of fix, that's the same code. So it is true that this is satisfied. Now we use the law here, the relational law, where we take this diagram as the precondition of that law, then this precondition. So P is fix, and F is the C of Q. And the law gives us this equation, which equivalently means, if you substitute what C of Q means here, this code, then CT of fix of Q is CT of Q, and that's for any Q. So CT of fix is CT. It's an interesting property. But if you apply this function CT, well, any value of this type, if you apply it to the fold data given by its own fix function, then so which is S of CT to CT, right? I'm just making it more apparent. So the fix function has the type S of CT to CT. Here I wrote it out, what CT is, but fix has this type signature. So if I apply this value to its own fix function, I get a value of type CT out. And this property shows that I get the same value out. I don't get a different value of type CT. And that's an interesting property. Now, if we apply the same relational law with P equals fix in any other F, then we have this. CT of fix is CT. And so we get F of CT equals CT of Q. So actually, F must be equal to C of Q, any F. So this, because C of Q is defined like this, it is a function CT going to CT of Q. So F actually must be equal to C of Q for any F. That is a direct consequence of this relational law. If you use it with P equals fix in any F, that's what you get. So we have proved that there is a unique function. So we will use this uniqueness property of the fold function to prove the isomorphism of the fix and unfix, so that fix and then unfix is identity, and unfix and then fix is identity. To prove that, we will use the trick that we will provide different fold data of different types and substitute that into the uniqueness property that we just proved to get a function that extracts data from CT, so this sort of function. And then we will automatically get that this function satisfies the compatibility property. So that's the plan. So the first thing we do is we look at the following fold data. So the function for the result value of type S of CT, and the function must have the type S of CT to S of CT. So one such function is the lifting of fix. So fix is S of CT to CT, and lifting it to S, we get this. So if we use this as fold data, then the corresponding unique function that we get by the property we just proved is a function of this type. If we use a definition here, then this is going to be this function. And this is exactly unfix of CT. This is the definition of unfix. So unfix, therefore, satisfies this equation, which now looks like this. Fix and then unfix equals this F map and then F map. Now this is a composition of two lifted functions. By the composition law of the functor S, we get this equal to a single F map of the composition of the two functions. In other words, we have proved that this equals this. So this is an interesting property, but this is not yet enough to prove that both of them are identity function. So now let's consider fix as fold data for the type CT. The corresponding unique function of type CT to CT is identity, because we know that CT of fix is CT. Now this, we can intuitively understand this as saying that there's only one way to extract the data from the type CT itself into the type CT. And for the list, it means that you're folding into a list, and there's only one way. You iterate over the list and you accumulate its data into a new list. So that's going to be an identity function from one list to another. However, we have another function, let's call it I, temporarily, of the same type, CT to CT. And that's a composition of unfix and fix. So unfix goes CT to S of CT, and then fix goes S of CT back to CT. So I has that type, and it also satisfies the compatibility property. This is because if you write that property out, you get this must be equal to this. But that's equal because that's, as we just proved, not equal to that. So the function I satisfies the compatibility property. The function I, therefore, is the same as this identity function, since there's only one function of type CT to CT that satisfies the compatibility property, given this fold data. So by uniqueness, it follows that I is identity, and so I was defined by unfix and unfix, so that is identity. So now we have proved that unfix and fix are inverses, and the other direction, fix and then unfix, it's just equal to that. So that's an F map of identity, and that's identity. And so this proves the isomorphism between CT and S of CT. So CT is a fixed point of this type equation. Another property is that it is the least fixed point, which means that for any other fixed point, T, that also satisfies that equation, there is a unique map from CT to T that satisfies the compatibility condition. Now, this compatibility condition can be also read as the condition that the fixed point recursion structures are preserved. So this map is not just some kind of embedding from CT to T, it's an embedding that is compatible with the recursion. So if you have some kind of folding from CT to some data and from T to some data, the same folding will work after you embed. An example of a different fixed point for the list, for example, is an infinite sequence. So infinite sequence is like a list of infinite length, if you wish, or a list of a stream, or stream that is not going to end, does not have a fixed length. Now, certainly that is not going to be the same as the list. And in fact, folding does not terminate on an infinite sequence. And so this type, the search encoding type, could not possibly represent the infinite sequence, because that is actually the fold function, the generalized fold function, and it has to terminate. And so for the example of list, the list or CT, the church encoding of that type with, as I showed with this functor, the church encoding is equivalent to the list of a finite length. The length is not known in advance, but it is finite. So if you use the church encoding as a definition of things, you're guaranteed to have a finite sequence. You're guaranteed that your fold will always terminate just by virtue of this type. So that's a very nice property. And there's actually a language called DAL And this language does not have type recursion, so it does not have an ability to define recursive types by induction, but it has functions with type parameters. So you can define the church encoding of recursive type. Note that this church encoding is not recursive. Non-recursive, the type is not recursive. None of the methods are recursive. The fix and unfix are not recursive. There is recursion there. It's hidden in a clever way by this type. The price is that it's much more complicated to work with this type, and the performance may be worse. So this is the example of the church encoding of recursive types. To prove the properties of the church encoding, which is that it is a fixed point and it is the least fixed point, we needed to use the full relational naturality law. The final application of relational naturality is here to simplify this complicated type. This type is a third order function because it has a function inside a function, argument inside a function. And you can see that this is similar to the church encoding. If we apply the church encoding to this recursive type definition, where there's a contravariant recursion scheme. So the recursion scheme is contravariant. This is usually not allowed or not recommended. But if you try to do that and use the church encoding, then you get this type. So T equivalent to S of T. With this S, you cannot really define it very well. So if you try to do the church encoding, you get this type. Now, actually, the church encoding doesn't give any non-trivial type. It gives just option K. So this is actually equivalent to option K under the usual restriction of full parametricity. So now we will prove that. This is a non-trivial proof. None of the usual methods work here, neither the Yoneda lemma, nor the wedge law, nor naturality laws. We'll see that. So first we define the isomorphisms, which we will prove to be isomorphisms. So we define functions in and out. So from option K to this type, and from this type to option K. Well, that's not so hard. The main idea is that this type must use a constant function here. There's no way to create an option K value out of a value of some unknown type A, other than just to always return the same value here. Ignore this argument and return always the same value. And if you do that, then you can do this double negation and get the value out. So this is how it works. So if you have a value of type option K, then you return a function that takes P. P has this type. This P is then applied to a constant function, returning just this constant value of option K. And so that gives you a value of type A. And if you have a value of this type, you apply that value to the type option K. So then you get an argument of type option K to option K. And then you use that argument on the fixed value none of type option. And then you get the correct type out. So we need to prove that this composition is identity. So O out of in of some option K is equal to some option K. And that is pretty straightforward. You just substitute the code and you simplify and you get the value out. We also have to prove that in of out of some h, where h is any function of this type, again gives you the same h. Now that is actually not straightforward. If you just substitute the code, you get this. Now this is not equal to h. If it were equal to h, you would have a function with code p goes to h of p. But instead of h of p, you have this. So the only way to prove that this is true, that this is still equal, is to have a law for h that says that h must take its argument p and apply that p to a constant function. So that argument p will have this type. It will be a higher order function whose argument is this function of this type. So it will apply p to a constant function of this type. Now, if we look at this code, that's what it's happening here. That's what's happening. It's applying p to a constant function of the right type. And this constant function has this value, which is just a constant. And we need to prove that this function is the same as h. So the first attempt to do that is we just use a naturality law. Let's notice that this type signature actually has the form g of a to a, where g of a is this type constructor and it is covariant. It is covariant in a. And so this is really a function that has a naturality law. And the law looks like this. For any f of type x to y, and for any value gx of type g of x, we have this equation. And this is a typical naturality law. If you substitute what the map function is for the functor g is this, then you have this code. Not very easy, but that's just how it is. So the naturality law can be written out like this. So, but what we need is a law of this form. H of p equals p of some constant function. So let's try to put that into that form. Let's try to say that f is a something that returns this p of that thing. So then this will be equal to f of h of x of gx. So x will be option k, and f will be this, and then gx will be this function that applies to none, that is the argument of this in here. And so then f of h of x or gx, this side of the law, is what we need, exactly what we need. But the right-hand side of the law is not what we need. It is if you use the same f and the same gx, of course, you have to, then you get this. Now this, what we need is h of a of p, not of h of a of this. So that would have looked like that. K goes to p of k, instead of k going to p of some constant function. So we need, so we got somewhere, we got halfway to the proof, but we need a more powerful law than the naturality law. And that is going to be the relational naturality law. So the intuition that we have is that we must prove that this function h of this type, if it's fully parametric, it must apply its argument of this type always necessarily to a constant function of this type. Now, we can express that in terms of relations somehow, but how? So let's try to do that. We expect that these functions h of p and h of q are equal whenever p and q are related in some way, such that p of k equals q of k for all constant functions k. So then if you apply them only to constant functions, if the code of h is such that it only applies them to constant functions, then this equality will be sufficient. We will never apply those functions p and q to anything but constant functions. And so we will not notice that they're different in some other way. And that should be equal. So if we can prove this somehow, then it will follow that h of p is actually equal to p applied to a certain constant function. So let's try to express this intuition via relations, and that is not trivial. So the trick is to use the correct relation R in the relational naturality law. So here's the relation, some relation that works for this proof, namely something that is almost identity. So it's a relation between A and A, and it's defined for any fixed value A of type A in this way. So X and Y is in this relation when either X equals Y or X equals A. So when X equals A, Y can be anything. It's still related to that X. Otherwise, they should be equal. Now, this is a many-to-many relation, generally. At this point, we are making an assumption that A is not a void type. So there are some values of type A that we can take and we can write down and so on. Now, if A is a void type, we need a different argument. So we'll do that at the end. Let's, for now, assume that A is not void. So then there are values of type A. We can take one, and then we can make this relation. So now let's lift this relation, R of A. So for every A, there will be a different relation, R of A, defined like this. So let's lift that relation to this type constructor. And that gives us a naturality law of H, which is written like this. Now this is quite long, because I've written out all the details. This is the relation R applied to H of P. So this is here. Then there is a pair function mapper for all arguments such that blah, and then again a pair function mapper here for all xy such that this, and we have kx equals L of y, and so on. Now this is an equality because this is this type. K is of type A to option K, L is of type A to option K. So because it's a constant type, not depending on A, so the corresponding lifting is an identity relation. So the values K of X and L of Y must be equal. There's no possibility of that. So let's look at that. Suppose K of X equals L of Y for all X and Y such that they are in the relation R. So it means that for all Y, L of Y equals K of A, the same value. So L is a constant function. And then also K of Y equals to L of Y for all other Y, not equal to A. And so K and L are actually the same constant function. Now this, we assume that, well, maybe that there are values of type A not equal to A. Now, if A is a unit type, then there isn't any Y, but then all functions are constant functions. So that is fine. So we see that this relation between functions K and L is satisfied for any constant functions K and L that are the same and for no other functions. So we can simplify the relational law saying that this for all P and Q such that for all constant functions K, so we can eliminate L. So for all constant functions K, either P of K equals Q of K or P of K equals A. And then if this is true, then this must be true. So this is the relational law. Now this is what we're going to use now in order to prove what we need. So if we need to prove this equation. That was the last that remains to be proved. Now the relational law has the form H of P equals H of Q, or H of P equals A for all P and Q such that. So let's make it so that this law reproduces this equation. So now Q, we choose Q like this. And then let's check that the precondition holds. So that for all P and Q, we had this here. For all P and Q such that for all constant functions, blah, blah. Let's check. We can check. It's easy. Let's take any constant functions and then like this, that returns some fixed value, and compute Q of K. We do that, and we get basically P of K. So for a constant function K, P of K always equals Q of K. Now what we need is a condition that's they're either equal or this is equal to A. Well, we just proved that they're just equal. So that's fine. So the precondition holds. Therefore, we get this. And now this holds for any chosen A. But the definition of Q does not depend on A. So we can, so this law is holding for all H, for all P, and for all A. And so we can say, we can choose an A. Given P, we choose an A that is not equal to H of P. And then this will be false, and this must hold. So then we obtain this as required. So this completes the proof. This was the last step, that this is equal. And then we have that left-hand side equal to right-hand side. And then finally, we get that in out of H equals H. So this shows the type isomorphism. Now, what I said about the type A being non-void, if type A is void, then there's a void to option K to void to void. Now, this is certainly satisfied by our code. So this is not void itself. So we can have a function of this type, have a value of this type. Void to, so let's write it down. So it's void. In Scala, it's called nothing, right? Nothing to option K, to nothing, to nothing. Now, we can implement a function of this type if we, so this is a unit. This is just a function that returns, that never needs to return any value. That function exists. And then if we have a function from this to nothing, then we apply that to this argument which exists, and we get nothing. Now this is purely formal. So there is code of this type, it's not void. However, we are required to produce fully parametric code of this type. And if A is not void, that code is restricted so that it is given by in of some out K, opt K. So this code is restricted to functions that are equivalent to getting to holding a value of option K, getting a constant function here, and so on. The same code works for void type. So choosing A as void type does not give any additional restrictions onto the functions H. And so it does not change the fact that each value option K gives me one value of this type, and each value of this type gives me one value of option K. There are no additional restrictions coming from the void type, so we don't really have to worry about it. So this completes the proof that the type equivalence holds between this f of k and option k, which means that the church encoding of this invalid definition of recursive type with contravariant recursion scheme doesn't give anything interesting. It gives you, again, the type option k, and so it's not any kind of new type. And this is to say that the church encoding works correctly for covariant recursion schemes. We just proved that, but it does not work with contravariant recursion schemes. Here's a counterexample. not to say that contravariant recursion schemes are somehow useful. I believe they're not useful at all, and they should not be used. But this is a specific example of how we can illustrate this by using the relational naturality law. So to summarize, we have proved that fully parametric code always satisfies a certain number of laws. Usually these are naturality laws, but in the general case, when the type constructors become complicated, like they are in this example, naturality laws are insufficient, or even they don't exist. Instead, one needs to use relational naturality laws, and that's a very powerful technique. Relational parametricity is a proof technique for the parametricity theorems, and the relational naturality law is a proof technique for more difficult cases. Now, I would like to notice that relational parametricity has a steep learning curve. There's a lot to learn. And the result of using relational parametricity is a relation that may be difficult to interpret as a property of code. It is a property of relations, which may not be even expressible as a single equation. One cannot also write code that manipulates relations directly. So all calculations and derivations have to be done by hand symbolically, or using proof assistance, that is, symbolic manipulation programs. But in many cases, as I showed, naturality laws and the wedge law give shortcuts. So they are easy to write down. They don't have to go to the relational parametricity law and then back, and just directly can write down naturality law, the wedge law, and see if that helps. That helps in many cases, like in the Yoneda lemma, and then you can prove a lot of type equivalence, like, for example, flat map and flatten, and so on. But a few proofs in functional programming cannot go just with naturality laws. They require the full power of the relational naturality law, and some examples of these proofs are high order functions with type parameters and the church encoding of recursive types. So in my upcoming book, I have full details and full derivations of all these results.